I remember this used to have a belt clip. But they didn't.
They didn't. And that's why they failed.
Or Intel won. That's why we have Intel now rather than NAC.
Well, that CEO was like, no one's going to need computers.
So we're going to have a little bit of blather just so that we can establish levels. And the first piece of blather that we'd like to talk about is coming soon, in just about 20 minutes, is this exciting talk on bit banging the VGA.
We are alive.
And we are live. Welcome to the pre-show of the Silicon Valley Fourth Interest Group. But before we get to Mr. Bowman, we're going to have introductions, announcements, rumors, gossip, and stuff.
Can you move the screen a little bit to the right?
Yes.
I didn't actually touch it, so it's not my fault.
Okay, that's great. Thank you so much, John.
All right. So there I was today on the way to the Silicon Valley Fourth Interest Group meeting in downtown Palo Alto, or near downtown Palo Alto. They have two downtowns. There's what used to be the town of Mayfield. And on the way to Mayfield from Oregon Expressway, you can pass by the actual statue of Tesla. So I recommend that to you if you can't actually make it to see the actual statue. It's on the internet. And if you take the long way around coming to the meeting, you'll go by the Gates of Hell. Very nice Rodin piece. Gates of Hell open 24 hours for your convenience. I guess around the back there's a little door. I guess that's the service entrance of Hell.
Backstage.
Backstage of Hell, Dave Jaffe says. Well, welcome to the Silicon Valley Fourth Interest Group meeting for September. And welcome to those of you who are here in person and those of you who are joining us on the web, both now and later in time. We've got an exciting day, exciting afternoon planned. I don't know if that's too strong a word. But first, anyone have rumors, announcements, gossip, slander, libel, blather?
I've discovered a nice little GUI generation tool called Glade. It happens to be language independent, although you still have to use GDK libraries to get it to run. But all you have to do there is you can create your GUI, then all you have to do is do all the callbacks necessary. And I would like to, yesterday I did all my callbacks using Python, and I was thinking, wow, maybe I could do this using Forth. So how would that be to be able to have a GUI that is running Forth?
That'd be like way cool. And you know what? That brings up another issue that I'd like to discuss, and that is Fourth Day. And I think that there's just enough time, John, for you to get that working before Fourth Day. And you can give us 10 exciting minutes on that subject? Or, even better, you can give us 10 exciting minutes of how it blew up in your face and didn't work worth a damn. It's always more fun anyway. So, speaking of fourth day.
The Sam just got the ESP32 E4 version.
That is way cool.
That was he worked all day yesterday, all night. And finally we got the E4 running on the ESP32, which is a newer version of the ESP8266. And it got the 2 CPU cores in it.
Uh-huh.
And I think it has Bluetooth on top of the regular Wi-Fi.
And if one would want to learn more about this, where would one go?
So far, this version so far is only working on serial port. Later, maybe next version for Wi-Fi.
With Wi-Fi.
Do you have source code on GitHub or a how-to or anything like that? Or
Just one file. I derived from the old version ESP.
well, if you could make a how-to that might be usable to people that are out in the world, send it to Dave and we'll put it up on the...
We'll give it to Dave and have him circulate it.
That'd be great.
Yeah, it's only one file.
It might be fun to hear about that at fourth day. So, 2 things I wanted to say about fourth day. If you don't have your talk already, well, you better get started getting it ready because it's in November, not very long from now. I've been sort of slacking off in terms of putting up announcements. One of the things was I didn't want to be participating in any traffic on comp.lang.forth on that subject. But what brought it to mind was there was a somewhat troubling announcement about Chuck Moore withdrawing from participation in the fourth community or some words to that effect. The only thing I know about that personally is that Chuck Moore has been asked. Yes, he's coming. He's coming, in fact, to the point where he's asking me questions about the projector. So yes, Chuck Moore will be here for fourth day. And so will I, and so will many of you, and I'm looking forward to it. So, Dennis, do you want to talk about...
Now, there was a rumor that Chuck is retiring. May or may not be true. I know his Facebook page is gone. He seems to be gotten out of social media. He never participated much anyways. So I don't know what extent it is. And I don't know what we want to do about it. Maybe nothing. But I open it up to the group. If you have an idea of if anything that we want to do something for fourth, for Chuck, this fourth day, let us know in the mailing list. Figure out what we want to do. I'm not volunteering. I have 0 or less time these days. But I just bring it up as something we might want to do. He's done a lot for us. We wouldn't be here without him. And I don't know. It was just, we can't let the opportunity go.
So that brings up another issue that I'd like to ask the assembled multitudes. First of all, if you're on the internet watching us on YouTube or whatever, we have an email discussion list. You're welcome to join it. Go to Google and say, when is the next SVFIG meeting? And it'll bring you to the agenda page, and it has my email address on it. Send me an email. Say you want to be on the list. I'll send it on to the list moderator, and it'll all be happy. I'm confident it'll all be happy. Which brings the question to mind, how many of you are not on the list, not on the discussion list. All right. I'll take your word for it. If you're not on the list and just don't want to raise your hand, see George at the break and he'll get you on there. One of the things we were talking about last month was what to do with the huge amount of money that we're going to get from the sale of t-shirts. Well, it's not that huge, but at least it'll be a start for something, perhaps. And one of the things I thought we could spend money on that's sort of bubbled to the top of my personal list is a banner for participation in things like Maker Faire. And I think that was brought to the fore at the last Maker Faire. They said, well, I thought we had a banner. Didn't we used to have a banner? Where's the banner? And the answer was, I think, I don't think we actually ever had a banner. And if we did, we've long since lost it, since we don't keep track of anything, since we don't actually exist. Anyway, if you have something else you think we should spend money on, we can discuss it on the discussion list. Does anyone else have any rumors, gossip, announcements, slander, libel? Okay then. If you're interested in podcasts, complete non sequitur, nothing to do with anything. There's a service called Stitcher. It's an aggregator. If for whatever reason you don't want to get your podcasts off of iTunes or anywhere else, Stitcher has a lot of NPR stuff. It has a lot of BBC, some old stuff. It's got Gilbert Gottfried's podcast. That particular one comes in 2 flavors. There's the premium podcast that you pay a little money for all of Stitcher's premium content. And then there's the plain old for everybody, it's free. For example, Wait, Wait, Don't Tell Me is a radio program, but they also put it up on Stitcher so you can listen to it at your convenience off of your MP3 player. Dating myself. They have Paula Poundstone's program live from the Poundstone Institute, which is a hoot. She looks at scientific studies that are actual, legitimate, real scientific studies, and looks at them in a civilian with a civilian perspective. A man in the street or a person in the street look at the way these things are done and what they're saying and how goofy it is that somebody actually spent money to look into some of this stuff, which is pretty bizarre. So, anyway, I didn't see anybody raising their hand saying, ooh, I have this exciting thing I want to tell you about some fourth-related stuff. So, on that cheerful note, unless somebody else has a podcast they'd like to tout or some other... It's Bowman time, yes. Let's get James moseying on up to the front. And, this is where I invoke that statement on the agenda that says, do we stick to the schedule? Well, yeah, sort of. Sometimes we're a little fast, sometimes we're a little slow. A little bit.
top one, page. Is there a full screen? Oh, there's the full screen icon right at the top there. Those two, those
Oh, this
surely,
one?
surely. Ah,
Oh, that might work.
okay.
Never had to do that before.
Just figuring out where to zoom to.
All right, so this is something I hacked on maybe 2 or 3 years ago. I think time's flown. And one of the first things I did with the Green Arrays board was looking at driving VGA displays directly. That is no external components. And what I was going to show, was a bit of talk and then a live demo showing the thing driving the display. But it turns out driving a really long VGA cable is beyond the GA144's IOs. Maybe a few inches would be the maximum. So you're going to have to use your imagination and imagine I'm showing these things live being generated in GA144. Okay. Yep. One more. Thanks. So VGA is old. Can anybody guess who was president when VGA was invented? That's it. That's impressive, John. Yeah, so 1987. So there's not a lot of stuff from 1987 that we still have around us, but VGA lives on. It never retires. I think maybe because it just works. So we have VGA connectors. They were officially retired in 2016. That's when the consortium said that VGA is done. Stop using it. But that's right. Enforcement is limited. And I think the reason we keep on is because it's super robust. It looks like it's this ancient DB15 connector, but the important parts are just the top 3 pins, which are red, green, and blue. And then these 2 pins here are H-sync and V-sync, and that's it. So you've got these 5 signals with analog stuff going on them. There's no weird protocol or content protection or anything going on with VGA. It is super simple. Thanks, Kevin. Yes. And VGA, when it came out, just had one mode, 644, 60 hertz with timing that put the pixel clock, that is how long you got between each pixel on the screen, at 40 nanoseconds. So that's 25 megahertz pixel clock. And when it came out, computers were really slow. Like the PC was 4.77 megahertz. So obviously video frequencies are much higher than instruction frequencies, but 25 megahertz has stayed the same, and our available execution rates for computers has increased. So it used to be the case that only hardware could generate a VGA signal, but these days lots of things can generate VGA signals because lots of things can run at 25 megahertz. The FPGA people have no trouble generating a 25 megahertz video signal for VGA, and a lot of CPU people try to generate VGA signals, but those CPU people have a bit of a problem in that if you've got, for example, a 25 megahertz CPU, then you've got one instruction for every pixel, which doesn't give you a lot of headroom as far as doing anything fancy for the pixels. So some of them can generate things like test patterns or reduced resolution images. Doing proper VGA is kind of tricky because you get into limits that you're running out of instruction cycles. It's also tricky code to do that CPU because of instruction. Right, you've got to time your instructions very accurately so that you can exactly hit, for example, the horizontal sync frequency. So it's quite fiddly stuff doing it in pure software on a conventional CPU. Thanks. But thanks to GA144, with its multiple CPUs running in a pipeline, becomes pretty simple. So here is my design document from the back of the napkin. Generate the pixels in one node, send the pixel data into a timing generator, which is in charge of doing the 25 megahertz timing. So the only thing it actually is ever dependent on is just making sure that the pixel generator feeds pixels fast enough. And then the timing generator will produce the analog output signals. So there's no tricky timing loops for generating horizontal or anything. That's all encapsulated in a separate system. And there's a nice pipeline. So long as every stage in the pipeline can operate at 25 megahertz, no problem. It's all simple. And here is my fantastic prototype. So I've taken the headers straight off the GA144. There really is no external going straight into a VGA connector. So the GA144 has a bunch of digital signals, but also a handful of analog outputs. So the analog outputs are driving the red, green, and blue signals here, and then a couple of digital signals are driving the horizontal and vertical sync. The analog outputs are kind of weird, but there are some voltage values which match the VGA requirements, and I'll be showing the colors that result in a moment. Okay, thanks. So this is where it all gets into implementation. So those yellow nodes at the top, those are R, G, and B analog output. Those are dedicated analog output nodes. And these two, 417 and 317, are the horizontal and vertical sync signals. Oh, thanks, Kevin.
Button right there with the green stripe.
So those are the video outputs. So the horizontal and vertical sync outputs. These two nodes here are the timing generator. So they're just clocking away at 25 megahertz. And then this giant block here is where all the interesting stuff happens, because that's the pixel generator. So the pixel RGB values are generated by these units, and then they feed individual pixels back onto 416. So 416 has a very easy life. It just accepts RGB values coming down the line from 415. And then 416 and 417 together generate, if you like, consecutive pixels which go to the output port. Those flow to the GPIOs on here, but then they're also sent north for the RGB value. So there's a packed RGB value which goes up north here for every pixel. 617 pulls out the red component, puts it on its analog output. Same with 717 for green and 713 for blue. So what you end up having is that 417 just generates output values, and they flow to these 4 output nodes to make the signals appear on the outside. Now, knowing a little bit about GA144, you'll point out that the blue is makes quite a long journey before it gets to the output. So the red is going to go out quite quickly, and the blue is going to come out a little time later. And if you look closely at the monitor, you can actually see this happening because it's a genuine delay.
What about the, what's that, 708?
That's the debug node. So that's the.
Debug node?
It just sits there.
So the other three to the right are RGB.
That's right. So these, you can see the wires here which connect these guys up to this network of things. So it's kind of interesting when you're programming GA144, you write some code, but you also have this sort of giant 2D layout where you've placed it. And in a sense, the layout plus the code is the program. And yeah. And so there is a flow here from the pixels down across here into the pixel generator and then back up to these port drivers here. And everything fits easily. It's all, when you partition it like that, there's no problem with the fact that they've only got 64 instructions each. It fits great. Pipelining it like this is also good for timing, because at 25 megahertz you maybe get, depending on temperature, you maybe only get 8 instructions per pixel. So 8 instructions isn't actually that many on a pipeline. You've got to do like a fetch from a port, which can be 2 instructions, and a write to another port. That's 2 instructions. You've used half your budget already just moving stuff around. But keeping it super short and keeping the tasks focused on each pipeline node means it actually does fit inside its 40 nanosecond timing. But what I started with was I just used to generate a very simple test pattern, like alternating white and black to get something going here on 415, and then feed those pixels in. It's much more interesting if you have more time for every pixel. If you have 8 clocks for every pixel, then you can generate a super simple pattern, maybe alternating white and black. If you have 1,000 clocks per pixel, then you can generate something much more interesting. Here's one way of increasing the number of clocks per pixel, is just to do them in parallel in batches of 16. So 500 through 515 are the pixel generators. So each of them in turn generates pixels 0 through 15 for the first line of the screen. And then they send it down to these. This is just a bunch of wire nodes which collect them all and then stream them out here. While they're streaming out, 500 and 515 are then working on the second span of 16 pixels. So effectively you get 16 times the time for each node. And if that hadn't been enough, I would have just added more nodes in here. Obviously, there's a whole bunch of chip. There could have been a serpentine path going down here to maybe do 48 pixels, all being gathered and then conveyed down in the pipeline. And this really takes the heat off the timing, because then you've got, instead of 40 nanoseconds, 640 nanoseconds to actually complete each pixel. So these guys have plenty of time to do something fancy for pixel generation. These conveyor nodes are all fairly similar, but not quite the same. So 415, for example, is the final pixel. That's pixel number 15. So what it has to do is it has to carry pixels 0 through 14, which arrive to its left, over to the right-hand side. And then for the 15th pixel, that's the one that was actually generated for its slot. So convey 14 from the left and then source that last pixel from the right. It's just a little loop on GA144, so it's all super simple. Same for example, for 409. It needs to pick up 8 pixels from its left and then send the pixel from above, and then that's it. So they're all slightly different, and it's all just plumbing to arrange this data flow so that this 16 eventually gets conveyed into the pixel timing engine. Okay. Any questions on the layout? Because that's where that's really the heart of the thing.
Just a real quick one. It's 713, that one. How come you didn't put it over?
Oh, because only a few nodes have dedicated analog outputs.
Oh, okay.
They're like scattered willy-nilly across the chip.
Sorry, it's been a while.
Willy-nilly, yes. All right, so use your imagination. This is what it would look like if it was actually running, if the monitor had liked it. So this is the test pattern, so I'm sort of trying out the analog values. We should go back. I've still got more to say about this. Okay, so how do these things generate their color values? Well, it's just like fourth salon. Each of them gets an XY input. It has a little counter for XY because it's 64480, and it's always 64480. And it procedurally generates its pixel color from the XY coordinate, just as the fourth salon haikus do. So each of them is counting, and they always know which pixel they're on. For example, this guy starts on pixel 0 and then counts across in 16s. And this guy starts on pixel 1, becomes 17, 33, etc., because it's always in chunks of 16. So it's super easy for them to maintain an internal counter to keep track of where they are. And then it's nice for pixel generation. There's no state. It just procedurally generates the color value from its XY coordinates. All right, so this one is just selecting red, green, and blue. It's doing a variable number of shifts to select the color value, depending on what the X coordinate is, and then the Y coordinate is just the brightness. Color ramps. Okay. All right. So I've given you everything you need to know. This is quiz time. Okay, so block of code takes X, Y on the stack as inputs. Its output is a single 18-bit number. It's kind of nice having an 18-bit computer for color because it's 666 as a color format. So that's a single word that comes out, which is low bits are red and the high bits are blue with the green in the middle. Okay. So in this assembler syntax, this does an over, so it picks up the X coordinate, and then at P32, these two go together. So that's ANDing the X coordinate with 32. This then does the same with the Y. This block of 2 X's shifts that value 6 bits to the left, and then OR is XOR.
Or is XOR?
Yes, GA144 is perfectly simple. OR is XOR. I wish I'd thought of it. Yeah. Yeah, I mean, GA144 has no OR instruction. It was deemed superfluous, and it's true, you don't really need it. So it takes the X coordinates, X coordinate, takes bit 5 out of it, takes the Y coordinate and takes bit 5 out of it, shifts the Y coordinate into the green channel with these shifts, and then it XORs those two things together. That's what it looks like. Right. So each of these is, right, so this is just, if you just look at the red channel, that's just bit 5 of the X coordinate.
It's basically what it's doing is it's each one of the raster lines, you're just computing each one of the pixels, just pumping them out.
So it's just brute force. There's plenty of compute capacity, so there's no need to have like state variables or anything. You can just procedurally generate it from the XY coordinate. Just like Haiku. I mean, it burns a lot of electricity, but... Okay, so that was that one. I have something even more impressive.
You did that? Oh.
Well, me with the computer, yeah. That's right. So it takes the low bits of the X and the Y coordinate. This is, I would view fourth Haiku as just a warm-up for this exercise, because after you've done a few. So it takes the low bits of the X and Y coordinate. So that's just a modulo or a binary AND. And then compute the distance function from a center point within each 32 by 32 square. And that's just 2 multiplies and an add, so still plenty of time. And to get the circle effect, I could have done a square root, but square root's kind of long. So I might have run out of time. So instead, I just look it up. So what you're seeing there is the distance squared. So that is effectively a graph of r squared. And then I used something incredibly old school to turn it into random numbers, which is just look it up in the ROM. This is the first 8 or so instructions in memory. So I take this radius value, which is in the range 0 through 9 or something, and then look it up in RAM, I think. It's my own program. It's the program's own code. And as it happens, it's a beautiful set of colors. So job done. So all this is all being done on the fly. So again, there's no frame buffer. This is all just being computed directly from the XY coordinates in that block of 16 nodes. Okay. All right. Any? That's all I put on because that's the only one that would fit on a slide. It's all in GitHub, so the links are on there. Okay. All right, and then the last one is a random pattern. So it's just a hash function. So take the X coordinate and the Y coordinate and drop some of the low bits so things turn into 8 by 8 pixel tiles, and then feed the X coordinate and the Y coordinates into a big hash function, which hopefully produces an interesting pattern. So it's sort of pseudo-random but also stable. So I haven't done any. The thing about GA144 code is that you get to a certain point and it gets quite hard to work on. You think, oh, normally when you're writing code, you get to a certain point and then things are a little bit tricky and then they get easier, right? It's working now, I can add another feature. But on GA144, it gets to a point where it's working and it gets quite hard to modify it. Been my big trouble with GA144 is even though years and years of coding on it, gets to a certain point and the difficulty becomes more, not less. So what I wanted to do, and I started trying to do this week in my spare moments, was as in Fourth Salon has a frame variable on the stack, right? It has frame and X and Y. And adding that for animation would be kind of cool because then you could write things could slide around and stuff. You've got a time term. But it's very hard. And arranging the loops was just too much for me. And that's what the GA144 is like. It just doesn't seem to scale up to a certain point of complexity. And I'm still struggling with how to do that.
They get controlled by interactivity rather than a loop.
Yeah, I mean, one thing to do would be to have a broadcast node, which could source from a pin or be a counter or a random generator.
Just use it as a variable.
Right. Yeah. So yeah, that's would have involved a floor plan change to do that.
Either walk over the question or repeat the question.
Oh, sorry.
Choices.
So the question was, could an external pin control be used as an input into the graphics? Could. But changing the floor plan is always a bit dicey on GA144 because it's a giant rethink. And normally I like to make small incremental changes, which are fairly safe. But with a floor plan change, everything changes. You're kind of stuck in this non-working state until you've got the floor plan resolved. So once again, that's another challenge on GA144. Quite difficult to work with. And that is it for my VGA on GA144. Any other questions, or was that it?
You send a link to your GitHub to Dave for the meeting notes.
Will do.
One question. What's stand next to Ting?
Ting, yes.
Yeah, this always remind me of the MUP21, where Chuck did a 20-bit CPU and a memory coprocessor and the video coprocessor.
Right.
Yeah, that reminds me of that.
Right.
It was marvelous that it's VGA. And it requires one clock, 3.5 megahertz clock, which clock out all the colors.
Oh, it was NTSC generation?
NTSC, I'm sorry.
Oh, yeah.
NTSC.
Right.
It's a little bit less than SVFIG, but
Yeah.
it was marvelous.
Right.
It was able to
Right.
use one chip and 3 coprocessors in it and doing pretty much what you were doing here.
Right,
But
yeah.
he's reading
Yeah.
data from the DRAM.
Right. So,
And he gave the priority for the video coprocessor. So if the video coprocessor needs something, it will read. And when it finishes reading, it gives the processor to the CPU to do whatever the CPU wants.
right.
But then it kind of interlaced very nicely.
Right.
But I hate to ask him for the code for the video coprocessor.
Yeah.
But it was, the video compressor is only a couple of lines of pixel, couple of lines of cells.
Right.
And the memory compressor is a couple of lines. Wow.
Yeah. Yeah.
So nice.
A trick that I learned with GA144 to deal with the floor plan
Huh.
is one, I do have a package that draws the floor plan and annotates the nodes. That helps. But the biggest difference is that if you write things so that the left, right, up, down is sort of generic, then you load what you want. Load generic code into your nodes.
Right.
Rather than trying to do everything real tightly within your node, put them into another file,
Right.
to another folder thing. And that way you can duplicate across the line.
Right.
It allows the duplication.
Yeah.
And that helps a lot.
Yes.
It doesn't solve it.
I have been doing that. I mean the other, that's one thing is to keep is not to embed the code in the node, and it's just to keep it somewhere else. Also using wire nodes while I'm reshuffling.
Yes.
Yes,
use your wires.
Yeah.
Just move a little bit at a time.
Yeah.
Wire everything.
Right.
Could you do something like as if it were like a logic synthesis? You have a tool that, or words that would synthesize to that sort of layer of indirect, as if it were a logic synthesis tool in a way? I don't really know much about the GA144.
It's kind of true. We don't really care about up, down, left, right. We just care about the topology.
Right. That's all. If you factor out the left, right, up, down,
right,
it sort of works.
Yeah.
And you can sort of plant things anywhere you want.
Yeah.
But it's a pain.
Yeah. That's quite difficult to think about. Yeah.
And we never got. We always had the idea that we could come up with a visual editor to do things, to do your floor planning, but we never got there.
Right.
We never had enough time to get there. I'm not sure how. But it takes more than trying to do it on a GA144. And that's where Chuck went. He wanted to do it right on the chip.
Oh. Right.
Yeah.
Right. Michael.
You mentioned the delay. Could you stand next to it?
Okay. All right. Yep.
Prepared to. There's a delay for the emission of the pixel. I think it was blue from 713.
Yeah.
Did you say you could see it?
Yeah. You can see color fringes on the VGA output.
Okay. Have you considered using the shared GPIO pin between 713 and 717? Synchronizing the emission?
I guess, I could have done. Yeah. I didn't consider it, but yeah, that would work, probably. Yeah. Yeah.
I was wondering if there's maybe a reason why that could.
Right. Yeah. Seems quite difficult to use, that synchronizing pin.
Yeah.
Yeah.
Can you control it from?
Yeah. But.
I mean, it's treated just like a GPIO, right?
Right. Yeah. Okay. All right. I think that's it.
We are in a little bit of a break right at the moment while we test out some stuff and sell t-shirts. See you in a bit.
It's on now?
Whoever says talk.
Okay, yeah. Okay. Let's see. Slides out of order. Hi guys, I'm Michael. I'm talking about green arrays simulation tools. Mostly talking about visualizations and various debug methods. I'm going to be doing a green arrays watch update as well. But first, so again, what exactly a green arrays chip is. First, I want to talk about the F18 computer. F18 computer is small, it's fast, it's efficient. I've compared it to the first 18 nanometer computer I could find online, an Intel Celeron from 2002. Someone's going to get mad at me for comparison, I'm sure, but the point here is just that it's small. It's a very teeny computer. It has 32 instructions, around 20,000 transistors, burns less than 5 milliwatts. It's an order of, or 2-3 magnitude difference from all the other numbers, except for the speed. It's a quick little computer. But what can you do with a computer this small? You can get 144 of them, and you can make green arrays, GA144. It's really just a multi-computer, just a matrix of F18 computers, each one talking to its neighbors, up, down, left, and right. And that's really the essence of the computer. That's what it is when you're programming it. A few of them around the edge have GPIO pins, some other specialty stuff. But that's basically it, a field of little computers. And having a chip like this, a unique chip like this, presents itself with sort of a unique approach to software development and a unique kind of problems that it's good at solving, and different sort of problems that it's bad at solving, and different sort of difficulties. And dealing with that is really why I've been building simulation tools to kind of make my life easier as I program it. But before I get into those, I want to talk about the green arrays GA144 watch that we've been working on. I'll give you guys an update. The last time I talked about this, presented these slides. The biggest addition here is that James Bowman has contributed the virtual machine that he presented last time to it, which has been a huge step forward for the project. This was, or is, the computer, the watch. Got a G144, low power e-ink display, some flash, accelerometer, all sorts of stuff to, make the watch smart. Here's what's new. First, the virtual machine is integrated. I had some more platform support. You can sleep, talk to the buttons. There's graphics RAM for storing graphics primitives outside of the main virtual machine RAM, so it doesn't fill it all up. And you can, everything's now integrated, so you can, in a high-level fourth, you can talk down and kind of control the screen, draw stuff to it, refresh it. And I have a little video. It can now kind of tell the time. This is running without delay, or it's with a lot of delay. Am I not connected? I did download this just in case it crapped out. Oh geez. Well, it's a binary clock. It's the easiest kind of clock and the least useful. But the point is that it kind of tells the time, I guess. Am I closing the right thing here? All right. Yeah, so this is where the code is at. If you're interested in contributing to this or helping out, we'd love to have more contributors, or let one of us know. It's now that we have this virtual machine, you can, or will be able to soon, create graphics and watch applications in high-level Forth. So you don't want to bother yourself with F18 assembly, which I don't think a lot of people do, but you want a cool Forth machine on your wrist. This is more of a possibility. You can program in high-level Forth that I think most people are used to. Most people in this room. All right. So I'm going to demo for the rest of the time some simulation. Actually, I don't want to. Yeah, I do. So first one is, how do you run an array Forth application on your laptop like you would a regular program? So what I'm going to look at here is, what did I want to demo here? Let's see. Test. This. Yeah. So this is the Fibonacci sequence. And because green arrays has no print or anything, we have this additional construct, show t, which prints the top of the stack. So we can actually get something useful while we're running it. And to run this, we can run it with GA run this test print. No, that was the wrong one, A Forth. All right, print stuff. This syntax here with the double exclamation point just calls a list function. So you can define your own. That's defined here in this file that's included, test print. It's pretty simple. It's just a list macro. Sorry, not Forth. That is called whenever, after this instruction before it executes, it'll call that function. It passes it the variable node, which is bound to the object, the F18 computer that called it. So you can query it, change its state, basically do whatever you want with it. In this case, just print the top of the stack.
This kind language?
Lisp?
This,
Yeah.
is that right?
Yeah, Lisp. Yeah. Emacs, let's be specific. So, let's see. Yeah. So, let's get a little more complicated and look at some actual testbed stuff you can do with this. So, first we're going to look at a test. Yeah. Moving up completely into Lisp is really where you have, I suppose, the most power, of course, because the whole thing is written in Lisp. So you can instantiate new green arrays instances. Is this big enough? Yeah, you can instantiate new green arrays instances, compile it and load code. In this case, we're just adding two numbers. Assemble and load a boot stream. You can connect multiple chips together with this connect pin syntax. And execute that. So in this test, we're just testing. This is kind of the configuration that you have on the green arrays eval board, where you have the test and the host and the target chip, and you can load the boot stream through node 300 to boot up the target chip. So after it finished boots, it queries that node, the target chip, and makes sure the memory and registers stack is all as it would be if it executed that code. So another sort of neat thing we can have, instead of connecting pins together, you can attach virtual probes to the pins. And really what this is based on, actually, yeah, to go back to the last one, this function, connect pins, what it's really doing is installing a handler. There's two functions that are relevant here, the set GPIO handler and set pin. One allows you to react to changes in the GPIO pin, and the other one allows you to set it. So you can just link them together and it passes the state changes along. We can also save that value, kind of create a virtual digital analyzer with connect probe. And that records the values. Probe save dumps it out into this file, which we're just going to run here. It just makes a Python program. So run probe demo. This is really just a random. So after it finishes executing, it graphs what is displayed here. This is just a test. It's just random. But we can get rid of that, load nothing. This is node 715, so it's going to try and boot over the SPI flash. You can see what it does there, and it obviously failed. Yeah, I haven't actually, I'm not sure how useful this really is or if there's a problem with it, because I've always found it more useful to use a real logic analyzer. What else? Yeah. So what's more interesting, or more powerful, I suppose, is interactive simulation. I showed some of this last time. I'm going to demo. Yeah, so this is basically, this is one version of what it looks like. This is the, this program is the graphics display RAM on the watch. The virtual machine would go on the top. It passes the values down, they get stored in the bottom here. That should then get passed along to along the graphics pipeline. In this view, it's displaying all the activity since it started executing. So when it first starts, you can see along the peripheral, there's the nodes that try and boot themselves. As the program advances, you can see the data getting passed along the wire. The boot nodes start to fade, and then it spins in a while, sending the data out of the RAM to what would be the graphics pipeline, but that's just getting dumped. So let's look at the full watch. So instead of run, you pass sim. In this case, we're looking at the virtual machine. Right. So this is, right, up here is the virtual machine that James talked to us about a few times back, I think. Was that last month? Oh, whatever. So this is 705 is fetch, decode, execute, return stack. And down here is RAM. There's a wire to pass node data back up to 708 for async out. And then the wire down to the graphics RAM. And so this is, we are executing this. Let's look at the file, vm.aforth. There's some display bug here. Okay. So we've defined, because we want to simulate the flash, and we don't want to simulate it, don't want to simulate the bit banging of it. This is just faster to do it this way. Instead of calling 24O, which would send that command out, instead we're going to call setAdder, which we defined here. This is just like the function I showed you with for printing the top of the stack, except a little more complicated. It's setAdder references the dumped flash, which is just stored in this format that it loads up. We set their address, it retrieves the correct fragment, saves that for the next time you call readline or read next, and then returns the next one in the list. In this case, it pushes it onto the top of the stack. And so that's everything to simulate it. The program that we're going to be running in swap forth here. Fourth mode. All right. So after we boot, we're going to admit a number, and then we're going to left shift something more times than necessary. And we're going to call this rectangle function, which is going to create a rectangle and send that down to RAM, and then redraw it. So, yeah. So when you're in the display, this is the usage view. Nodes are highlighted based on how much code is in them. You can switch to the activity view, which is A, no activity now. Hit C to continue, and it lights up as it runs, right? So now it has sent out, I've just stopped it. It sent out this value to 708. This has done the if I visit the emit function. Right. Now, stop it again. You see the whole virtual machine has stopped except for the execute node. If we look into execute, we can look into the beginning here and see what it's executing. It's just doing that shift. It's copied the code into the node and is executing it at native speeds. And the rest of the virtual machine is completely dead right now. It's completely suspended. Once that's done, continuing, now it's copying values to and from the RAM. These are the rectangle values. Now those and send those down now to the fixed RAM. It's going to do that a few times for each one of these shapes. And yeah. So now it has called update. So now it would be updating the screen. But instead, it's just dumping the values. Yeah. I think that's it from there. Source level debugging. So we're going to look at okay. This is just the RAM portion, just the display RAM portion. And this is the source for it. The display RAM, right, it's just a wire down to the display RAM. The 204 and 104 are control nodes. 103 contains, the actual data is stored in 105. It's stored sequentially in the first part of RAM, in kind of like an array, so it can be read sequentially out fast to the virtual machine because the entire list of primitives needs to be dumped every time. 103 contains mappings from IDs to the locations of each primitive, so we can access them randomly, delete them, update or change them. So you can switch to the usage mode or activity mode, start to run it, right? Now if we hit, the key is, I think, P. Yeah. So now when we run it, it can highlight in the source the corresponding location. Let me see, how do I? Okay, I make this a little smaller. Yeah. So normally you have the compiled view. You can step through it. Like you can see over here, the current location. Dupe is the next instruction to be executed. So you can step through it, but that location of that instruction in the source file can be highlighted as well as we execute, like this. All right. This is kind of like GDB style debugging. Now stop that we can step through. See the values getting passed down the wires. It's just called new. Right. So you can track, because any sort of program that you have in a green arrays chip is really multiple programs that it's one program that you split across multiple computers. And this allows you to track them all, kind of where each program is simultaneously in the source. Yeah. I think it's kind of fun to watch. What else do we have? And now I'm going to show you the graphics recognition application. This was something that we did. This was a chlorophyll program we did a few years ago. I just found it again and decided to run it because it's pretty fun to look at. So we can have a look at that. And this is the kind of the basic overview of what we have. Values are read in through I2C from the accelerometer. Filtered values are passed to each one of the classifiers for each type of gesture. They're quantized. Right, we've taken three value vectors. They're quantized to one of the groups, and they're passed along to an HHM hidden Markov model classifier, and the probability is printed to the laptop. This is how it's implemented, how the layout was implemented. This is from chlorophyll. I'll make this bigger. Oh well. Okay. So the main parts here is this section here. These contain the quantizer vectors, the quantization vectors. They get passed along to this core part, which performs all the logic from each step of the forward algorithm. This is all standard probability stuff. And the values for the A, B, and PI vectors are stored along the edge here for A, at the bottom for B, and right here for PI. So let's open that up. Where is this? Right. So here it is. You can see the replication of each one of the models. They're identical. The top here is what passes a list of kind of faked accelerometer values for testing. This section is the filtering, and 608 is where the values are sent out. So let's run it. Right. So now it's starting to filter it. It's doing the filtering. Passes the values down. Now the quantizer is running. This takes some of the longest time. It calculates a distance to each one of the quantization vectors and chooses the closest one. Right. So now it's getting values from the B arrays and A. Yeah. So that was one step. You can see the flurry of activity that happened afterwards. I believe was it shifting all the values to prevent overflow. But this repeats itself. I think typically 20 or 30 times per value, but potentially more than that. Or per gesture that's recognizing. That was the demo. We can simulate boot streams as well. here, let's look at the original one. Just pass it sim boot stream. Typically, there's no reason to do this. Oh, that's not good. It just takes a while. And displays a scratch buffer, which is kind of the dirty secret. No, there we go. So normally you wouldn't want to do this because it just takes a long time. When you simulate it, it just dumps the values straight into RAM and starts the simulation from there. But if you want to see what's actually happening when it loads the chip up, I have to start that over again. It's very slow to do the live updates, live activity updates. I think because it's refreshing the screen every time. It does a step. But it's typically not that slow. Here, so activity, right? You can see it start to copy it in. Each node programs the next node in sequence to pass the rest of the stream along. This is displaying the recent activity. If we switch to with T, we can toggle it to show the total activity, which kind of gives you a better sense in some cases of what's going on. But as it retracts, it's easier to see. I think it's more interesting to see the total activity. Or the recent activity. So now it's starting to retract with the application left behind. Right. Yeah, and there it is now running. Actually, I can kill that. Yeah, so I'm actually nearly out of stuff. There's a few other things, other little features and stuff. It's like you can print time estimates. This is of dubious quality. Somewhat support for the James Bowman's GA format. So you can load it up. You can print into that format. This is really just something I use for work with the watch because that's what we're using for it. And it's, but if that's what you prefer to use and you want to use a simulation for it, the support for it is there except for the prefixes, which means it's almost useless without modifying each one. Yeah. Yeah.
Could just load a boot stream, right?
Yeah, but who wants to do that every time? Well, I just showed you.
Oh, that was it.
Well, actually, it is a bit faster than that. It has some weird bug right now where it needs to step the whole chip to completion before it loads the boot stream. That's why it's kind of stuck right now when I'm loading it. But it takes a long time. Like you could see it snaking through, right? Just because it's updating the screen. But if you don't do that, then let's look at that. Yeah, it's done most of it already. Continue. Oh yeah, it's already finished. Yeah, it's not too bad, but yeah, maybe that's reasonable.
So another question regarding the boot. So do you have a copy of the ROM in the simulator?
Yeah. Yeah, I've dumped it out of my val board. So whatever's in there is in the simulator now. Yeah, if you're simulating it, I'll make it smaller. Right, you can see most nodes start up in ROM here, right? Warm, all this stuff is ROM. It's only nodes that I've loaded stuff into that it's in the lower areas. Right. So yeah, it's basically the same thing. Cool. Other questions, other things? I have a bit of time still, but I don't have a lot to fill it with. I did the watch first for a reason. Everyone's asleep.
He's going to have to either repeat the question or...
He's asking if I have James Bowman's fourth haiku thing. No, I don't. No, this is the little graphics things. I recall it vaguely from a presentation, but I haven't. No, maybe it could be adapted so you can have them on your watch or something. Sorry, what's that? Yeah, right now the display supports 32 like graphics primitives, like circles, rectangles. Is that it? I mean, right now there's no support for, set pixel x, y to some value. There's, but yeah. I mean, I hope in a little bit we'll get it to a point where, other people can write little things that might interest them on it, perhaps in the same sense, yeah, little apps and stuff. Of course, people need the hardware first, so we got to work on that. But yeah. Questions? It powers over a USB or from a laptop. It has power management on it. Yeah, so it should be able to, has its normal lithium LiPo battery that gets charged through the USB as well, I think. So it's got some little like battery management chip on it.
How much power did you say it consumes for
currently or in theory? Well, currently it's 20 milliamps, I think, which is really pretty terrible. It means that it's an equivalent of like 4 nodes running like in a tight loop. So obviously, if we want to show this thing off as sort of like a demonstration of the low power abilities of the green arrays chip, then we need to do better than that. But maybe there's some problem that I had in there. Maybe there's a lot of other chips on the board, so some of them might have come up in some state that's consuming more power than it should. I haven't looked at it at all, but it should be able to consume microamps. The display consumes a little bit of nothing. When it's suspended, it's waiting on the crystal. It's really doing nothing, or nothing significant. So it should be able to, if it's just like updating the seconds or something, or the display once a second, it should be able to go on, I would hope, for months. Yeah. I'd be excited if you wanted to come help with that. You could just take a watch apart and, yeah. But yeah, no, I hope it lasts for months. I've found some smartwatches that have an apparent battery life of like a month or so, and some sort of, I don't know what kind of standby mode, but that's what they advertise. So I'd certainly like to do far better than that. Cool. Any other comments or questions or?
Thank you very much. Thank you.
Testing, 1, 2. Testing, 1, 2. Awesome.
I'm beginning to trust the little bar.
Oh, nice. Well, in about 30 seconds, you'll hear me over the network, so. Okay, so I guess this concludes the break. My name is Sam Falvo. As some people know, I have invested a large amount of my time into a project called the Kestrel Computer. And there are various, what do I want to say? There are various incarnations of it, or generations, if you will. About 6 years ago, significant to this talk, I had started to work on a computer called the Kestrel 2, which was my first FPGA resident machine. In that, I developed the video core, I developed a keyboard port interface, I developed general purpose I/O, got everything working, and even developed a small 16-bit MISC minimal instruction set computer processor for it based on the Steamer 16. And again, everything worked pretty well, but as I was starting to write software for it for real, I quickly realized, oh crap, I'm running out of memory. It was so cramped that I could not successfully implement even an overlay system. I was running out of memory trying to come up with an overlay system. That's actually where my operating system STS comes from. It was part of that little project, and I'm happy that everything booted fine. But you know, the extent of the software that I could run was basically a slide presenter program that I called Milestone 5, because that was the 5th milestone application for it. And anything more sophisticated, like even a 4th interpreter, just no room. Because after carefully studying what was going on, I realized, oh, I'm investing about 48 bits on average per primitive operation, where that's defined as like an addition or memory fetch or store or whatever. So I was like, okay, I need access to external memory. It's not that I particularly care about instruction density, but I figure if I can access the 16 megs of external pseudo SDRAM on this FPGA board, then I would have enough space that I wouldn't have to care about instruction density and stuff like that, and I could just go ahead and do what I needed to do. And in the process of doing that, after about 3 years, I've finally realized, oh crap, I need to get a job and stuff. I had to put the project on the back burner. That eventually would have been the Kestrel 3, but unfortunately, like I said, I just didn't have the resources to invest in it. And between the Digilent Nexus 2 going out of production and Altera DE1, which uses SDRAM, which is probably even more complicated to use as a chip, you know, I just realized I just didn't have the intellectual capacity to invest in it, and plus not having good debugging and development tools kind of hurt me as well. So that was on the back burner about 3 years ago. I'm sorry, about a year ago is when I put it on the back burner, and now for the first time in about 3 years, the Kestrel 2 is booting again. Only this time, the highest risk part of getting a Kestrel 3 working, which was the main CPU, is now part of the Kestrel 2. So I'll go ahead and show you a little bit of details as to what's different there. So this is a synopsis of the difference between the original Kestrel 2, which was built around the 16-bit processor and the current Kestrel 2 DX. So as you can see, I had 32K of program RAM located starting at address 0, and then I have 16K of video RAM starting at address 48K, or yeah, 48K. And then in between, rather inconveniently I might add, I placed about 16K of space dedicated to I/O, out of which I was only using 4 bytes. But be that as it may. And it worked great. But right now I've decided, as part of my evolutionary approach to developing the Kestrel 3, I'm going to start with the Kestrel 2, which I know works, and just replace one piece at a time, in this case the processor. It's something I've wanted to do for a while, but like I said, originally I was having problems accessing RAM. But this time I was like, all right, let me focus specifically on using internal block memory. So now with the new processor, it is a 64-bit RISC-V, as I promised with the Kestrel 3. And it has significantly more memory space available to it. I've got 32K of space reserved for ROM, and it's actual honest-to-goodness ROM. Like, you'll notice that I don't have ROM listed in the original memory map. That's because I relied on the FPGA to, when it loaded its bit stream from Flash, it pre-populated block memory, and that was my boot image, so to speak. But in this particular case, I actually have a synthesized ROM. It's not even in block memory because I don't have enough block memory resources. But so this is synthesized and is largely the reason why it takes 11 minutes for this thing to synthesize. Next, I've got 48K of contiguous RAM at long last. I've got my 4 bytes of I/O from the original Kestrel 2. And then I have this expansion space, which is currently at 16 megabytes. The reality of, I list this as a 16 meg of expansion space. The reality is it's got 18 terabytes of expansion space because, it's a 64-bit processor. But yeah, this is kind of what I'm currently working with right now. This is not intended to be the final memory map for Kestrel 3, but again, this is just enough to get stuff going and getting more productive with things. So, let me see. Oh yeah, and in terms of I/O, there's actually one additional piece of I/O that I'm going to be adding as well, and that's going to be a synchronous serial interface adapter, which I mentioned briefly down here, but I don't go into too much detail. The other thing too is I'm using more bits on the GPIO output that I have. I'm using a pair of bits to control which chunk of RAM video is drawn from. Right now it defaults to the very beginning of video RAM, but if you want to, you could actually relocate that elsewhere for whatever reason. It was effectively free to implement, so I figured why not. Also, I'm using 2 input bits for horizontal and vertical sync detection as well. There is no interrupts, just like the original Kestrel 2, although the processor does support interrupts. I just don't use them right now. So what I'm going to do now is I'm going to actually boot up the Kestrel, and hopefully this video will... So right now I'm going to program the FPGA. I'm going to enter my incredibly long military grade password. And then I'm going to hit reset on the thing. And now this video should change over automatically, as I discovered today. Boom. So it is now waiting for input on the keyboard. And not 5 minutes ago, I'm sorry, not 8 minutes ago, because minute hand moved, I got SD card operation working. So I'm going to initialize, because by default it does. Fresh code, that's right. This is brand new code. This has been committed to the repository literally just about 8 minutes ago. And what I'm going to do now is I'm going to load into memory address up somewhere up in high RAM. I'm going to start my load from block 0 on SD card, and I'm going to load, in this case, we'll just say 16 sectors. So about 8K of data is going to be coming into memory. Keep in mind that all of these numbers are hexadecimal. This is a machine language monitor, so there is no decimal anywhere in this. This will take it a little bit, and it's done. So now if I do a memory dump, we see that we've got bytes. Now this is actually bootstrap code for the original Kestrel 2. But eventually I will populate this card with RISC-V code instead. But for the time being, this is, and you'll notice that this address is a full 64-bit address, and all bits are significant. If I attempt to read from or write to RAM that doesn't exist, I run the risk of deadlocking the machine because I don't have bus acknowledge logic for the entire address space. I just have it for the stuff that I showed you. So that's a good way of definitely crashing the machine if you want it. But let me show you. I actually have a backup of this image, but I can actually change memory. So I'm going to start at that address, and I'm just going to blow away the first 16 bytes there. So I'm going to blow that away. So now if I do that again, we see that that's written. So now I'm going to save, starting there at block 0, and I'm just going to save that one block. So now that's actually written to SD card at this point. So I should be able to reset. And notice how fast that comes up. God, that's so nice. So now I'm going to reinitialize the card because it's booted. This time I'm just going to read in that one block. Oh. Oh, too many zeros. So like I said, if you read from wrong address, there we go. Yep. So we actually have actual stored data. And also, if necessary, I can use the G command to go to different places, or it's actually a subroutine call, but traditionally G is for go to. So I'm going to go to address 0, and that will reboot the machine because I don't have any other programs that you can run. But if I did have binary image on SD card, you would I to initialize, use the L command to load a binary blob, and then G to run it. So this basically is a bootloader at this point. So as of 13 minutes ago, Kestrel 2 DX has finally gotten its first bootloader. Not terribly user-friendly, but this is, you may wonder, where did I get the name TIM from, especially if you're familiar with Commodore computers. TIM is the name of the original Commodore PET machine language monitor. It stands for Terminal Interface Monitor, and in this case I'm calling it TIM5 for TIM for RISC-V. It's actually written in C for now because I invest at most maybe about 3 or 4 hours a weekend into this project, so I don't really have a whole lot of time to invest in porting something like Forth, but that's going to be next on my list, especially now that I can actually load stuff from SD card. Every time I make a change to this ROM, it incurs a 15-minute resynthesis time because it has to resynthesize all of Verilog every time I change a ROM image. So now that I can load stuff from storage, this will make things a whole lot faster for me. This is a pretty big milestone for me. Another significant milestone, if I can use this segue to go into the second part of my talk, I'm going to dump the entire ROM contents that it has right now. And I want people to really pay attention to how fast it updates the screen, because I think this is pretty cool. Okay, so it looks like it's running with text mode functionality, right? This is probably about as fast as, well, I stand corrected. This is actually faster than an IBM AT running at 12 megahertz on a typical VGA display, thereabouts. And it's important to realize that there is no actual text mode. Just like the original Kestrel 2, this is a bitmap display. It's pushing bits, not bytes. The processor itself is clocked at 25 megahertz, but it typically takes an average of 5 clock cycles to execute a single instruction on this particular generation of processors. So I'm only getting approximately 5 to 6 million instructions per second throughput. This actually makes me pretty happy, because when I first designed the processor and mapped out its performance requirements, I specifically used the Commodore 64 as my benchmark. Using this has to feel to the user like you're using a Commodore 64. It cannot be slower. I would be happy if it were faster, but it was not realistic, right? So right now it's almost done here. But basically, this is basically updating every time it scrolls a line, updating the entire screen, you know, in part by doing a block copy and then filling in the text underneath. And this is involving a combination of byte level and word level access to bitmap memory. Now, the interesting thing is about this bitmap memory, thus leading us to our second part of the talk. Part of the reason why this is updating so fast is because the processor is a little endian processor. That is to say that when you access a 8-bit quantity at address 0, there's also a 16-bit quantity at address 0 and a 32-bit quantity at address 0. And that low-end byte will always appear in the same column. But and that on its own isn't sufficient really to make the graphics fast, because in the Commodore 64, all you had were 8 bits to work with, and the VIC chip, of course, fetched data at 8 bits at a time. So it made perfect sense to do the traditional thing, which was to assign bit 7 of a byte as the leftmost pixel of that byte, and bit 0 is the rightmost, because that's how you would draw it out on paper. It's how you read it. We're all left to right readers, and so forth. But it turns out that as soon as you have a processor that is 16 bits or 32 bits wide, and you do more sophisticated graphics operations like shifting, for example, if I were to draw a mouse pointer on this, for example, using the traditional MGIA layout, it would result in massive amounts of code. Basically, you would end up with your traditional blitter, then you would have to byte swap before you blit, and then you have to byte swap after you blit. And it just becomes a nightmare. And of course, calculating effective addresses on the bitmap becomes an issue as well. So what I did to simplify everything was I went into the MGIA source code, which is up on GitHub, and I deleted one character from the Verilog source code, and that one character was a little tilde, which inverts a counter in this particular case. So now I have it so that bit 0 is actually the leftmost pixel, and bit whatever is however many pixels across. So now I can access video memory with bytes, half words, words, or double words, 8, 16, 32, or 64 bits at a time. I can do whatever bit manipulation that I want in either an assembly or C or whatever, and it makes sense. And I can just use naturally calculated effective addresses, and as a result, it saves a lot of time on the processor, and that's in part why video display is as fast as it is. So basically, by matching how the MGIA fetches and treats memory to how the processor treats memory, eliminates a lot of cruft. It actually significantly simplifies a lot of stuff. So that's basically the updates that I wanted to give you.
So the Kestrel 2, first time it's actually been projected on this projector in about 3 years. It's alive again. Next step is to port STS or get some kind of operating environment running on it. I'm not sure quite what that looks like yet, but we'll find out soon enough. And of course, the moral lesson to be learned with respect to graphics is make sure that your video hardware and your processor is well matched. Eliminate all the impedances that you can, and holy cow, will it simplify your life when it comes to updating graphics. Any questions? I'll go him and then you. What's up?
So you said you cannot do bitwise operations because of the bit order that you chose?
So if I wanted to shift left, for example, if I wanted to take a block of pixels, say I fetch 16 bits at a time, right? If I wanted to shift left and on a little endian processor, I would have to swap the bytes. But then on top of that, I'd have to take the high order bits that come out of the top of the word and re-inject them into the low end of that word. And then I would have to byte swap again after that. Alternatively, I would have to do the shift, take bits out of individual byte columns and put them and wrap them around. So depending on how you do it, there's advantages and disadvantages to either way. But basically, either way you look at it, it's just extra time spent by the CPU that you just don't want it to do.
Yeah, so I remember reading some paper about how image editing software only updates or I don't know if they still do this, but only updates the differences in the image. I don't know if that would work for this question bitwise.
You would have to do, I mean, it would work in the sense that you could calculate the difference as an exclusive OR mask. What's that?
Would there be a benefit to it?
No, not for this, no. No, because you have to update the bitmap to calculate the difference mask to begin with. Once you have the difference mask, then you can store that in a file. And in fact, that's what the IFF anim format does on the Amiga. You start with a keyframe, and then every frame after that is just an exclusive OR mask that you apply over and over and over again to all your bitmaps. But in order to get to that exclusive OR, you still have to update that frame. And it's that updating of the frame that I want to optimize, especially since it's live. So right now I keep everything aligned on 8-bit boundary, but I do have code that I have written in Rust that will pixel align arbitrarily. So eventually I'll be running a GUI on this, I guess, once I get RAM. I guess, and that actually brings me to a good point. Why do I even bother with the Kestrel 2DX? I don't know if you saw in the original opening webpage there, but I've got a couple paragraphs that explain why. And what it is I want to use this computer as a workbench for developing RAM interfaces. So SRAM, I can get that working fairly easily, but I'm more interested in getting the pseudo-random the PSD RAM working on the Nexus 2 as well as the SD RAM on the DE1. Because Paul Hardy, who's a SVFIG member here, he basically donated the DE1 to me with the specific purpose of getting a Kestrel running on it. So it's definitely on my list. You know, I want to make sure that I do this right. And the reason I specifically want everything in this to run in block memory is so that I could take this design and port it to Altera and port it to other Xilinx or port it to ICE40 or whatever with minimum code changes. Because otherwise, like if I were to take this and it's assuming that it depended on external memory, if I moved this to Altera DE1, like half the modules that I had written already would end up needing changes. A lot of this stuff is actually pretty hardware dependent. So, you had a question? Oh, cool.
How did you end up getting SDH? Is that SDHC or SD?
It's just plain SD.
Plain SD?
Yeah, I still to this day cannot figure out how to get SDHC working. I know that Leon Wagner had sent some code to me a long time ago, maybe about 3-4 years, but I was just never able to get it to work. SDHC, as far as I'm aware, is a broken standard. It is, I've yet to find a vendor that actually complies with the spec as it's published.
Trouble getting it to work myself. I was doing some remote sensing network, and yeah, there's so many differences. It doesn't seem to comply to the standard really.
Yeah, and unfortunately, I'm actually kind of desperate to get SDHC working because that's my last SD card. Yes.
What computer did the code that Leon send you expect to run on? Is that like a PC?
It's a PC. Yeah, he sent it to me. It was SwiftX code, I believe. So whatever controller that SwiftX particular program targeted.
They're legion.
Yeah, there's tons of them.
He's got like 20 different processors that SwiftX will talk to.
Right.
But it may be worth asking Leon to talk to that, or send us some stuff that we can frutz with, or maybe even present on fourth day that as a topic.
Well, I would like it to run natively on the Kestrel, so that I can actually boot the Kestrel without needing any additional external hardware. But there's options. We can look into it, I guess. I do have a couple of Arduinos that are sitting on the shelf doing nothing right now. So if nothing else, I could probably take library code from Arduino and hopefully work with that as well.
Or use the Arduino as your card reader.
Long term with the Kestrel 3 in particular, it will not only be the card reader, but it will also be the keyboard and mouse interface. Because I want the core of the Kestrel 3 to be as isolated from PC peripherals as possible. Because I'm sick and tired of having standards go obsolete on me, and then holy crap, I have to change everything just to support some new arbitrary standard. And by everything, I mean not just Verilog, but also software that runs on it as well. So, yeah, definitely, I'm learning lessons from this. And when I said that the Kestrel 3 was architected more like an IBM mainframe than not, I mean it very seriously. Kestrel 3 is very different architecture from Kestrel 2. Any other questions? Well, if not, we are 15 minutes.
Can we take another short break?
Yeah.
Sam's
The other Sam.
Sam 1 and Sam 2. Why don't we have this Sam 2? What time do you leave? All right, no break.
All right, no break.
Hand off the mic. All right, thank you.
Well, I have to have hands on the mic in order to hand it off.
Set the mic down and step away.
Well, I got to move my stuff anyway, so. All right, I'm going to turn the mic off.
In your pocket. You need to enable your screen.
Function should be F4
Usually there's a screen,
screen
something.
like this. Yeah? Do I have?
Yeah, but how about F2?
F2. Function F2. Yeah? I don't know. Someone. F3. See, F2 seems. Excuse me. Is there anyone can help?
Okay. Can help with the screen thing.
We're centered on screen.
Seems that
Maybe you have to do the screen setup.
mouse control panel. Usually I use search. That's good. Control. Yeah, got it.
Okay.
Control panel. Yeah. So what's that? Display. Maybe. How about using this? I'm not sure. Is this? How about using this?
Oh, you have the VGA? Oh yeah, I can try that. The way around? Yeah.
Yeah. So, take out this. Pardon? I just.
There we go.
Oh yeah. Is that right? The.
I think that is without doubt.
Okay. Actually, I think I'm not really well prepared for present, but just demo some code and showing some special things there. So, firstly, our ESP32 E4 is derived from ESP4 version 44, the last version for the ESP 8266. Actually, I didn't really do too much things. Let's see the code. Actually, it's just a simple one file. That file the name is ESP32E4 version 1.1. Okay. The first version is 1.0. The last night we did, and this morning, today we changed a little bit. The code we firstly modify the code for ESP32 as well. Originally for previous device. Secondly, we ignore Wi-Fi and UDP since we didn't really familiar with the new environment. So and we modify the interpreter a little bit to aid input line echoing. Fourth, we ignored the tone since not yet implemented in 32. And I tried some code here on our Wi-Fi boy, the board here. The first code, the simplest demo is the blinking, right? So we try to let the LED to blink. The first thing is to set the direction of the pin, right? The LED pin on Wi-Fi boy could be a little bit different with others. The pin number is changed to 16, decimal 16. Here we use in hex 10. But a little bit surprised. Should be 1 as the output direction. But I didn't really work. So finally we found the output is 2. So we use put 2 as output direction to set the pin. So then once we set we select the pin direction as output, the LED will be turned on. See, the default is low. So to turn on the LED, the pin level low. Next, we use 1 as level high to turn off that pin, the LED. So we use we we use 1 and decimal 16 to pin out. So the LD will be turned off. And then we can turn on again, say use 0, 16, pin out to turn on the LED. Later, I have tried define some new words. Say define W to do a loop, big loop, as a waiting process, to wait some time. And define edge to turn off the LED, and use L to turn on the LED. We defined three new words, and later we defined a blinks, so that we can use 5 blinks to blink the LED 5 times. Okay, so let's try to see. Firstly, we use 2 10 in hex. When we put up the system, default base is hexadecimal. So we can go to the console. Go to the console, put the instruction send, and the LD is on. Means we'll have already set the direction out as the output. Then we can use 1 decimal 16 pin out to turn off the LED and send. The LED now is off. And then we can use 0 decimal 16 to pin out to turn on the LED again. Okay, turn on. And then I'm trying to change the base as hex. And then we define a wait, W. We define W as a new word to wait for a while. Okay, now we have a word W. Then we can define several others, 2 more. H to turn off for a while, and L to turn on for a while. Okay. Now we have 3 new words, W, H, and L. And then we want define links. using for next loop. Okay, so that we can use a number to specify how many times we want to blink. So that, okay, now we say 10, well, that 8. 8 blinks. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And this fourth is token threaded. So we can see the memory if you, let's see. In the file, in the program, in the code, there is an array called data. Means the virtual memory having all the tokens. And I put, okay, here, the data from 0, 0, 0, then 4, 8 lots. And the entry point is 180. 180. This is the entry point we first, when we boot up, jump to with our IP address is 18, and the token 6, or the value in the, or the integer in the cell, 4 bits cell. If the value, the integer value is less than 63, means 63, right? Integer 63. That means all the primitive token. So we have only 63 tokens. The primitive instruction. Other instruction will be high level, defined by column. Okay. So when we come to 18, this is do list, the high level word inner interpreter, do list. Then all the others will be the instruction. For the first instruction, 1838, it's a high-level column defined high-level words, CFA of the words. Probably that's I'm not sure what's that. But anyway, if we see all the memory code, actually we can simulate how the E4 system running. Okay. Let's see. Here. If we see, we'll give a word, type in words, we're going to see so far all the existing words defined, high level words defined, column words defined. Or the E4 stand, I'm not sure which standard version, E4. So we have already lots of words can be used to do something. The last night I have just tried some, but still have lots of words to be checked. Okay. See, I'm not sure. Is there any question? Oh, okay. You mean the Arduino space? Okay, let's see. Here. Sketch used 4. Yeah. Let's see. Mm-hmm. Yeah. Still have enough room for playing. So far we don't have Wi-Fi. We ignore our Wi-Fi first. Well, Dr. Ting already tried Wi-Fi with ESP 86. So later we probably but probably using different libraries, new libraries for 32. Okay. Thank you.
Where is this available?
Pardon?
Have you published this?
Yeah. I have emailed to some of our guides to test. Probably, if you want to try, I can email to someone.
Email the list.
To list.
If you email it to Dave or to me,
I'm not sure how.
Ting can send it on. We're going to be spreading this stuff around.
Is this ESP32 Wi-Fi boy?
Okay,
That's it? So we're going to try some wireless mic getting around and back up to go. Do you have
any address? Can I use email address? If you would you please type in the address?
I can't type in Chinese.
No. The receiver.
I wanted Kevin to look at the keyboard and see what the Chinese. There you go.
This keyboard actually has Chinese on it.
Well, actually, it already knows you.
Is that right? Okay.
There I am.
Okay. Then.
What is this? Things machine? It knows who I am. No ne'er-do-well, it says. Slacker. Person of dubious merit. EDM, actually, is the short form. So like I was saying, we're going to try out the wireless mic and dick around some.
Okay.
Thank you.
Done.
We're going to call it a day. Content,
I think that this should be able for not MCU 12E, probably. Is that familiar with you? Okay. But you have this, right? Okay, so you can try it. Actually, I do have some spare. If you anyone want to try this, I can. Okay, thank you. Thank you.
Mike.
Oh yeah.
Good. Thank you.
And folks, it looks like we're done for the day. Yes, no, we aren't kissing you all off. but I think we're done for the month. We'll see you next month. Bye-bye.